Good morning, everyone, and welcome to our third webinar, Digital Tools for Accelerated Materials Discovery. This webinar makes part of a bigger series called Next Gen Materials Europe's Digital Manufacturing Leap. And the key takeaway of this webinar is understanding the benefits and applications of digital simulation and modeling in material manufacturing and the discovery of new materials and properties. The focus is how we can significantly reduce the time and cost associated with developing new and improved materials to enhance our businesses and at the same time address some global challenges. Oops. Okay. Some obvious benefits that we can mention is faster development, also lower costs, sustainability through discovering greener materials and less waste and energy use, also competitiveness. This brings innovation to market faster and respond to demand more effectively. And we can talk also about the improved key performance indicators, such as time to market, so it's shorter development cycles, also R&D efficiency, cost per material innovation, material performance accuracy, and also an important, the environmental impact. So the EU goal with this is to enhance industrial competitiveness through digitalization. And our key strategies for this is Digital Europe program and the European Industrial Strategy, so both of them. And the EU action for this is championing digital technology adoption across manufacturing. And this is aligned with the EU strategy with digital tools in advanced material manufacturing. Our vision is more agile, more efficient, and resilient European industry. So this is the third webinar, as I told you. The fourth one will be on the 24th of June, and I can mention this later. And this is a series of webinars, and 3 projects are participating. 3 EU initiatives, Pioneer and MetaFacturing, which are our sister projects, and we are here together to share these relevant topics for materials manufacturing. In this case, digital tools for accelerated materials discovery. So we will have 3 presentations for the 3 projects, as I told you, DiMAT, Pioneer, and MetaFacturing. And I will present you our beautiful speakers for today. So we have Leonardo Cosma from CETMA. He's a simulation engineer there, based in Italy, and it's a partner from DiMAT projects. Also Harrison Ramirez, which is a doctor researcher in UPV, Universidad Politécnica de Valencia, and he is a partner in DiMAT project also. Then we have Bruna Moura, which is a researcher in low carbon and resource efficiency R&D unit in the ISKU. She's based in Porto currently. She represents MetaFacturing projects. Then Inés Pérez, she is an AI researcher for AIMEN Technology Center based near Vigo, and she represents the Pioneer projects. I'm Sara Canedo. I'm communication manager for the DiMAT project, and I work in F-Success Innovation. So now we will have a little discussion to be more dynamic and also to allow our speakers to talk a bit about these issues. So we prepared some questions for you. Maybe I will start with you, Inés. So I have here a question. How can we significantly reduce time and costs associated with developing new and improved materials to address pressing global challenges?
Well, hello everyone. In my opinion, the discovery of new materials or improvement of the existing ones typically ends with basic research. For example, when aiming to improve a material using a welding process, logical step is to study the existing materials, for example, evaluating the existing steels for the manufacturing process in question, understanding their composition, their key properties, and basically conduct a literature review, consult the material databases, the technical dataset, and so on. And this is normally followed by simulations or by experimental validation that they need to ensure the reliability of the result. We need to check the result with the existing ones in the literature. So my point is that a significant portion of the time invested in material research is spent searching for and understanding the existing data. So how can we reduce this? Well, in the past year, we have seen how artificial intelligence is revolutionizing this this fact. So I think we all know ChatGPT, for example. This is one of the most famous models of AI, and this can be for these literature searches and overall to establish relationships faster and gaining more time for actual research. So these models are called large language models. Nowadays, more and more initiatives are being used in all these language models. For example, in the material science, we have MatScholar or Chem Data Structure that are built to automate extraction of properties for materials. We have companies like Aries.ai. This is a company that provides artificial intelligence tool to automate the search in the data. And this not only stops here, because that language models not only stop at searching literature, but the architecture that has been built to develop that models, it's called transformers, and it's now improving the predictions that can be made with artificial intelligence. So, for example, that architecture is being used to gain better prediction of material properties based on the chemical composition of some elements, and we can check or we can predict new properties based on new chemical compositions, or representing better the molecules and so on. So, well, my final answer, I think, is that AI, artificial intelligence, is one important aspect to faster the time invested in research, and also the cost, because it can help us to do better simulations, to avoid redundant experiments, and that is one of the main costs of researching.
Okay, great answer. Thank you so much, Inés, for clarifying this to us. Next, I will pass to Harrison. So the question I have for you is, what is the traditional approach to materials production and discovery, and what is the potential of digital solutions to introduce a shift?
I think based on the experience of many different companies industry, traditionally, the material science and production have been sequential and experimental, using the trial and error methods. I think this is not anything unknown for no one, that, as the previous speaker says, that spending so much into trials, I said it in my word, this is how it has been done traditional. That is the approach. Regarding to the potential of this digital solution to introduce a shift, I think it has been already proven that it does possess the necessary element for positive impact. I mean, a high impact. For instance, and we have many, we can say the possibility of replicating materials behavior under real-world condition using the simulation, also using this approach. I think the potential is so high to provoke the, actually, indeed, is a fact, is provoking this shift, and also enabling predictive performance testing, virtual prototyping, and also life cycle assessment without going into these costly physical trials.
Okay. Thank you so much, Harrison, for your answer. Maybe we can go now for the third question, which is directed to Leonardo. Leonardo, what is the most tangible and immediate added value that digital simulation and modeling can bring to SMEs' materials development and manufacturing process? And also, this is a very extended question, what practical steps they can take to get started?
Well, thanks for the questions. Thanks for having me in this webinar. I think the most important added value of digital simulation is to shift the focus of the design process and also the speed of this shifting process. That's because today there is already a wide use of digital tools, like for example, all the computer-aided engineering tools guide the design process and optimize any kind of component in every field of the industry. But when it comes into materials, normally one has to make a choice before the design of the part, or one can make comparisons evaluating different materials. What can be truly a game changer is the idea of shifting the design process from the component level down to the material itself. And designing a specific material for a specific application can lead to significantly better outcomes in terms of performance and cost of the final product. And digital solutions like those developed in DiMAT or the other are instrumental in enabling this shift. What does it mean actually design a material? As Erickson was explaining before, normally this involves extensive physical testing, planning a campaign, producing the specimens, and often there is the need to outsource the entire process because most of the time the SMEs does not have testing facilities. Instead, using digital solutions, SMEs can carry out this work internally with little or zero investment. And this is beneficial for several reasons. The obvious one, of course, digital testing develops far more advantageous than physical testing in terms of time, cost, and resource needed. But most importantly, digital tools allow for the integration of a lot of workflow, algorithms, methodologies that can guide the design process. And this enables efficient exploration of all the possible solutions, ensuring that the final design is truly optimized. And finally, the digitalization of the material design process is the key to reduce the development time. So I was talking about the speed. The time also to improve the quality of new solutions. When it comes to practical steps in digital modeling simulation, I suggest first of all starting define the specific challenges and use cases that need to be addressed. And then explore the available options because there is a growing number of solution providers across all engineering industrial domains that can meet the specific needs. And of course, the teams behind DiMAT, MetaFacturing, or Pioneer Project are among them.
Great. Thank you so much, Leonardo, for your answer. Now we move to Bruna. So, Bruna, how do digital solutions for manufacturing specially contribute to achieving sustainability goals?
So, first of all, good morning, everyone, and thank you, Sara. I believe that's a good question. Digital solutions in manufacturing really play an important role in helping us achieving sustainability goals in many ways. I will only highlight a few of them, but there are many, many, many more. So, first of all, when trying to improve efficiency and reduce waste generation across different manufacturing processes, through, for example, the installation of different sensors in the production line, real-time data such as energy consumption, material usage, or even waste generated. This kind of data may be collected and may be integrated with AI and machine learning models, for example, to identify some inefficiencies or even optimize them accordingly. Example is when trying to enable circular economy. For example, based on that, we can consider different approaches. Firstly, we can use, for example, digital twins or generative AI to simulate and test design choices like repairing, reusing, or even recycling. Secondly, digital product lifecycle management, like may track manufactured products lifecycle from their design stage until the end of life. And finally, we can have digital platforms that can streamline reverse logistics, for example, making it much easier to collect and process returned or even end-of-life products, putting those materials back into the system instead of discarding them. And for example, another example is when tracking the carbon footprints, because there are some tools where we can track the carbon footprint along the life cycle of manufacturing processes. And also this data is important for companies to set reduction targets, for example, and comply with regulations, environmental regulations specifically. For example, the ESG reporting that nowadays is very known. So I think overall, although digital solutions also consumes energy, I know that, and I believe that people have to be aware of that. They have a huge potential towards manufacturing sustainability by all of these things, such as optimizing, reducing wastes, and even boosting the circular economy. And by doing all of this, I believe that digital solutions may contribute to several development goals, namely industry innovation and infrastructure, responsible consumption and production, and also climate change. So I believe it's good.
Yes, and as you referred, there are many more to to say and to speak about.
Yes, yes.
So last question for you. If the EU companies were to invest in one specific area of digital materials technology right now, which one would offer the greatest return in terms of market competitiveness and sustainable innovation for Europe? What do you think?
May I comment in that, Sara?
Sorry? I cannot hear you very well, Harrison. What did you?
Yes, can you hear me now?
Yes, perfect.
Okay, just asking for having a comment regarding today's last question, if may I.
Yes.
And I think it's a good question. And although materials for clean technology application are at the top of the list of the UE interest, this investment probably doesn't have a specific area. I should say that it must go into the reduction of the R&D timeline and cost for new material development. And why do I say it doesn't have a specific area, in my opinion? Because there are many areas of interest and they are important to society. For example, let's say the energy, clean energy application, as I said before, is one of them. The health, but also let's mention the packaging industry. So if we apply those into those sectors, I think it would be beneficial. And that's why I said there is a specific area in which making this huge investment.
Okay, thank you for your comment. Has anyone has anything to add?
Just to cite a specific sector, I think that because of course Verizon said that it is there is every sector can be beneficial. I think especially in the semiconductor sector, that could be one of the most promising in terms of return on investment, because given the huge scale of the digital transformation that is currently underway in all Europe, also there is a growing market in various sectors. I can cite space and defense for obvious reasons, but just one of the sectors. Also, I think that in this area we could support the Europe strategic autonomy, reducing the need to import critical materials and critical technologies.
Okay, Thank you so much. Bruna, you have something to say. I saw your...
I just want to agree with Leonardo. I believe that there are huge and different sectors, but I believe that those who are very dependent on the critical raw material provided by European Union are critical to increase our competitiveness and also our resilience, because we depend a lot of other countries to do. Yeah. And
Thank you
also,
so-
I believe that when trying to adopt these kind of technologies, also jointly assess the sustainability of the different approaches. I think that it's something important just to guarantee that the new options are better than the ones that already exist.
Okay, thank you so much for the insightful discussion between you. We can continue after the presentations if you wish for, because those are very hot topics, as you know. So now let's start with the presentation. So first we have the DiMAT presentation given by Leonardo and Harrison. So the floor is yours.
Okay, thank you, Sara. Okay, just a very short introduction to the DiMAT project. The DiMAT project has developed several tools for the modeling, simulation, and optimization in each stage of the material value chain. We're talking about 9 different toolkits, software solutions that are grouped in 3 suites, as you can see in the slide. The first one is for the data management and assessment. The second one for the modeling and design of the materials before the manufacturing process. And the third one for the simulation and optimization in the manufacturing stage. Now, on the next slide, please, I will present a specific use case that we have handled using some of the digital tools developed by DiMAT. We are talking about the manufacturing of a drone and specifically an unmanned aerial vehicle, which is made a traditional composite material, which means carbon fiber reinforced polymer. The aim was to increase the sustainability and also the performance, and specifically redesign its materials, shifting from traditional carbon composite to flax fibers and recycled carbon fiber composite. So, how have we proceeded? I can go on the next slide, please. We have used some solution developed in DiMAT. In this specific use case, our focus was on optimizing both the material properties and the manufacturing process. For the material properties, we used DiMAT toolkits for 2 specific tasks, the virtual testing and the correlation analysis. Okay, virtual testing involves using numerical models to replicate experimental tests. And in this way, we've analyzed several materials, solutions, and formulations without the need to set up a costly and time-consuming physical testing campaign. And in just a few hours, we've been able to identify a new optimized material for the drone component we were working on. And along the way, we also use toolkits for the data analysis, specifically for correlation analysis, to determine which formulation had the greatest impact. And this helped us understand which variable to adjust to achieve the best possible outcome. Another area we worked on was optimizing the manufacturing process, and I leave the floor to Harrison for further details on this topic.
Thank you, Leonardo. Thank you, Sara. If you can go to the next slide, please.
Yes.
Okay, regarding to this specific case of the DiMAT project, in the following slides, I will introduce this segment of the project in which the advanced composite material transformation process is simulated, and specifically the curing process of the epoxy inside of the transformation or manufacturing of this composite material for the drone. And a question, why are we speaking about the process simulations when our title is the tool for advanced, accelerated material discovery? Well, By discovering new material, it is necessary to know their behavior under a specific condition. In this regard, and taking as a starting point the knowledge that we have about existing material, and we are speaking about internally, let's say the behavior of the molecule and so on, chemically and even more. We have the possibility of predicting the behavior of those material under a specific condition. And this is where our mechanical properties simulator inside of the optimization and simulation suite of DiMAT takes a place. First, we decided to go in an approach to simulate the curing resin in a single geometry that is well known that we can handle easily. But after applying this concept to more complex geometry of this drone component, we identify some inefficiency. So the first step was the modification of the solver used in the simulation. The modification of this solver consistent into integrating a new equation for the energy and transfer, and also to evaluate the evolution of this curing resin degree. After applying this new solver to more complex geometry, the previous slide was showing one component of this cover, we were able to achieve more than 90% of coincidence of the results, simulated results, with the one obtained in the experimental part. All of those simulations were integrated into a simulation routine, and after that we were able to compile it and created our toolkit to simulate the curing resin. Can you go to the next slide, please? And this is how it looks like, the dashboard of our toolkit for predicting the curing resin degree. Visualize how the curing degree is going into the time. For example, here we have the input, we put the name, we have the maximum temperature in which we will be using this resin, the time of stay, and the heat ramp. Also, we're able to upload on a specific geometry that we will be using, and the material. The backend that is on this toolkit already bring the material properties and also all the element that is needed for the geometry, let's say the mesh and so on. If we go to the next slide, you will see the dashboard, how it looks after having the results of this simulation. From one side, on the right, you can see the cure evolution. That is the percentage of cure versus the time. How long it will take to reach the 100%. Because as one of the key points into the composite material and the resin, composite and epoxy resin, is that the optimal curing cycle would be the one that guaranteed 100% of curing through the entire geometry. Said so, if we evaluate that according to the curve of evolution, we don't achieve the one, is go from 0 to 1, in which 1 represents 100% of curing, of course. So we know that the condition in which we are trying to cure the resin is the proper one. So we go again into the dashboard, the first one, we change the parameter, and we send the simulation once again until we get one. Also, we are able to identify the energy index, which represent the energy consumption in the curing process. And now, Leonardo.
Yes, just to tell the end of the story, let's say, what we have achieved so far. In terms of weight, we have a reduction of the 9%, and this is a really good result because it allows for the increase of the payload of the drone. And also, 8% of the drone right now is made by the recycled carbon fibers. And these are not the definitive result. The project is ongoing. We have optimized just a couple of all the drone components that you can see. We are confident that we can achieve a 20% in mass reduction and at least a 30% of use of renewable materials. Even so, these preliminary results already demonstrate the significant impact that the material-oriented design can have in practical application like this one. And also they highlight how digital solutions like that we have developed in DiMAT can be effective tools in supporting these activities. So thank you, and that's all for the DiMAT project demonstration.
Thank you so much, Haris and Leonardo, for your presentation. Now let's move on to Bruna.
Thank you, Sara. So I will talk a little bit about the MetaFacturing project. MetaFacturing is an Eurozone or Europe project that started in January 2023 and will end this year in December. And this project focuses on the digitized tool chain for metal part production, which aims to enhance resilience by using recycled materials, reduce operator costs, and minimize scrap and out of specification parts. The vision here is to create a versatile digital twin-based frame setup and control that meets the needs of large metal parts manufacturing. So basically it focuses on effectively using parts and process data to improve time to market and also product quality. So next slide, please. And as I highlight in the first part of this webinar, it's important also to guarantee the sustainability of these digital innovations. So within the scope of work package 4, task 4.5, named lifecycle analysis and lifecycle costing, aimed to improve decision making by understanding the potential benefits of the project developments by assessing both the environmental impacts and the operational costs associated with the two use cases being investigating across the project. There are the casting and the welding processes. And these two use cases were assessed through the first year until now by different methodologies like life cycle assessment and life cycle costing to ensure the beneficiaries or to evaluate the beneficiaries at the environmental and the economic perspectives. So next slide, please. These both methodologies, LCA and LCC, shared the same system boundaries and also the functional unities along all the processes. And for this system, we assumed the cradle to gate approach. That means that all the impacts since the raw material extraction until the gate of the producer of the parts were accounted for. We assumed two different functional unities according to the different use cases. So for the casting use case, we assumed that one finished part of 1 kilogram, and for welding use case, we assumed seam of 1 meter. We assume these functional unities because we had different scenarios with different scales. So we decide to normalize this to be more or less compared. So at the end, we evaluate different scenarios. We had the business as usual scenario at industrial scale, that is the current status of the plants. And then we analyze the developments of the MetaFacturing by assessing the environmental economic performance of the first and the second trials at the lab scale. And then with the lessons learned in the lab scale, we also modeled some theoretical scenarios at the industrial scale to compare these lessons learned and the benefits of the project with the current status of the production plan. So if we go to the next slide, we can see just a brief of the main results that we achieved until now, until this stage. So for the casting use case regarding the environmental assessment, this this study showed that the aluminum ingots significantly contributes for the environmental impacts in the business as usual scenario that accounts for more than 80% of the impacts. And in the labs trials, we had that wastewater was the main hotspot in this process because operates in a open loop. So that's why. And also this assessment also pointed out that there are benefits in using fully recycled materials in metal part manufacturing, because when we studied the second trials of the lab scale, we had a fully recycled part, and we can achieve a potential reduction of 31% of the impacts when compared with the first lab. And finally, economically, material costs were the main cost drivers for all scenarios. When studying the welding use case through the environmental analysis, the results showed that aluminium wire was the main hotspot of the process in all scenarios, accounting for more than 50% of the impacts. And also we conclude that the different configurations in the process may also affect the environmental impact. So this is an issue to consider of and to think about it. And also regarding the life cycle costing, this analysis indicated that labor costs for this specific use case was the main cost driver. Next slide, please. And finally, regarding the theoretical scenarios, we also want to highlight some main results in here. Basically, regarding the environmental analysis for the casting use case, we achieve the potential reduction of 27% and 31% by reducing bad parts by 20% yearly, and also using 20% more recycled raw materials, aluminium in this case. And for the welding use case, when we model a scenario with a reduction in with a 20% reduction in bad parts produced annually, we achieved a potential environmental reduction of 0.2% of the impacts. On the other hand, the economic assessment at this stage revealed that the cost reduction is not as meaningful as the environmental, at least for the casting use case. But nevertheless, I believe that the potential benefits, economic benefits in both these use cases may be greater than these initially calculated when further analyzed. So, in a nutshell, I believe that the results from these sustainability studies highlight the importance of the MetaFacturing project and its all ongoing developments. So, it's all from my side. Thank you very much for listening. And if you are interested in more detail about the project, feel free to follow us through the website or even at LinkedIn. And we will also attend the SNS event in Germany in September. So for those who are willing to join us, please feel free to join us on our booth. So that's all, and thank you for the opportunity.
Thank you, Bruna. Thank you so much. Now we will pass to Pioneer, represented by Inés Pérez. So the floor is yours.
Thanks. Next slide, please. So what is Pioneer? Well, Pioneer is a European project that wants to create an interoperable digital pipeline to support a design by simulation optimization framework. And with this, we want to ensure all the data flow across the material value chains. This meaning the design, the simulation, the production planning, the manufacturing, and also the quality. With this, we also want to connect the materials modeling with the materials characterization, the simulation part, the digital twins, and of course, the data-driven models. The next slide, please. So Pioneer is also involved in reducing the time associated with improving materials, and more concrete, is involved in reducing the time needed for the simulation of material performance. So to run these simulations, we need input data that typically we need to search in the literature. In Pioneer, one of the tasks is to develop an artificial intelligence tool capable of retrieving not manually, automatically actually, material property from the literature, and also structure it so it can be used for these simulation works. And this is going to be demonstrated through two industrial use cases. One is the MX3D use case that is focused on the technology of wire arc additive manufacturing, and it involves simulations about the ER110 and ER120 filler metals. And then we have the Marelli use case that is dedicated to the development of an upper controller. This is a component in a vehicle front suspension system. And right now, for these components, the current solutions rely on metallic materials or in hybrid metal composite combinations. But in Pioneer, we want to also evaluate the performance of sheet molding compounds materials. All of this will be integrated with DiMAT standard, that is an interface designed to exchange the simulation data across diverse softwares. So in the next slide, you can see this with a bit, thank you, with a bit more detail. So in the slide, you can see a screenshot of these DiMAT files showing the inputs needed for running a simulation. And you can see that we need the value for the density that it's right now being, it's missing this value right now. So the idea is to check in the literature for this value in different documents. And we are doing that using AI. And then we are using that information to be structured and connected in a database that will fill that value in the DiMAT. So then we can run the simulations. Next slide, please. So how are we working with that? So the first step is to collect a bunch of documents. Right now we are doing this manually, so we are searching for these documents and downloading them manually, but this is something that we want to improve. And then we need to make these PDFs more readable for the machine and for the model. So we need to use something called PDF parsers. There are several options. For this project, we are using Docklink and Structure and PDF Plumber. These are made in Python. And then we can download this information or transform this information in PDFs to more suitable formats like Markdown or dictionaries. So all this information is going to be passed to a large language model that can be ChatGPT, but in this case, we use open source models like Llama or Mistral because, well, for security. And at this step, we have something, we have an answer like for this document, the tensile strength is 700 megapascals at 20 degrees. If we want information about tensile strength, you can input the property that you want information, and that's the answer. So then we do some post-processing to store this information into value and unit, and also to standardize everything to the international system of units. And of course, we do some statistics to filter the possible outliers. So in the next slide, the flow that from this PDF, we can conduct all this analysis and all these AI steps, and fill and create this database with the different information for different sources. And then we can compute the average value or the value that is more suitable for these cases. And with that, we can fill this DiMAT and just run the simulation more efficiently and faster. And then I have listed some technical challenges involved in all this work. The first one is the standardization of PDF parsing strategies. This is because PDF is mainly used for visualized information, but not for extracting the information for the models. And this results in that each PDF can be very different one for another. We have very different layouts in the documents, and this makes challenging for these automated tools to extract the information. So to mitigate this, we have working on creating a benchmark of several parsers to evaluate how well they extract different layouts. You can see in the figure some results. Next slide, you can see another technical challenge was the integration of the tabular data, because the information that is inside tables and for the materials, all information is mainly stored in tables. Complicated to understand for these models because is organized in rows and in columns, in 2-dimensional, let's say. And on the other hand, the text is only organized 1-dimensional. We read it like a line, not 2 lines. So these language models are trained in text, not in tables, and they struggle to understand the relationship between the columns and the table and the rows. And that's why we need to pre-process a bit this information, because at the same time that these models have to understand this tabular information, they also have to map it with the queries of the user that sometimes can be a bit abstract. So what we have done is to before the extraction, we pre-process this information inside tables using a large language model to first interpret this table and transform it into a more natural language representation. You can see in the slide an example of original that has a first line with the material, the density, then a second one with aluminium, a value, a second line with copper and another value. And the idea is to transform this raw format into phrases, like aluminium has a density of 2, and in comparison, copper, it has a higher density of 8. And to do that, we use prompt engineering, that it's about how you tell these models to use that information. So we can do it using examples or only detailing very much the instructions, and the way you tell these instructions to the model affect in the output. And finally, in the next slide, another important challenge was the evaluation of all of these results, because determining if an answer is good or not is a subjective thing, because what appears relevant to me maybe is not for you, or also the completeness of a response can vary depending on my expectations or my domain expertise. But also it is difficult, if we have a wrong answer, it is difficult to know if the answer is wrong, because we are not retrieving the information needed for construct that answer, or if we have that information, but we are not creating or are using that information correctly. So this is an active area of research in AI right now. And we're involved in creating several metrics, like you can see that we have used statistics to detect outliers, but we are also using ranker models to gain confidence in the retrieval part, and also developing a custom metric to detect the kind of errors that we can get. And overall, this is all. Thank you all.
Thank you so much, Inés, for your presentation. Thank you to all the speakers and to all the attendees that were here and joined us for this third webinar. So I just want you to let you know that the fourth webinar will be on the 24th of June. So we count on you, and you will hear from us soon in our social media. I hope you follow DiMAT, Pioneer, and also MetaFacturing. And I also want to let you know that DiMAT will organize a workshop in the ICE conference in Valencia on the 18th of June. So we are searching for SMEs that are interested in digital solutions for material manufacturing. And well, if you know someone in Valencia that wants to attend, that it's interested, SMEs, it's the target we are looking for. So 18th of June, we will be there. It's free. For the ICE conference is paid, but for our workshop and cocktail is free. So if you want to join us, you are more than welcome. So thank you all once again, and I hope to see you in the next webinar. So have a very nice day. And yeah, that's basically it. Thank you all.
Thanks to you, Sara,
Thank you.
for organizing this.
Thank you.